Hi everyone, I'm Hanbin from UB. Today I will introduce our MobiCom work, PDVocal, towards privacy-preserving Parkinson disease detection using non-speech body sounds. Parkinson disease is basically a degenerative disorder of the central nervous system. In 2015, it affected about 6.2 million people and resulted in about 170,400 deaths globally. And early detection and treatment is the only effective way that help relieve pain, slow down the disease progression, and improve quality of life and extend the lifespan. However, early detection is difficult. A lot of people nowadays would say that a clinical solution can achieve early detection. Actually, they do provide a very accurate PD detection. However, these approaches require PD specialists or complex sensors that are not accessible in daily life. And statistics shows that about people usually not will seek a clinical diagnosis until the mid stage, by which around 70% of neurons have been permanently impaired. And to address such inaccessibility, people are trying to develop some non-clinical approaches. For example, considering that speech impairments present from early stages, one method tries to develop a voice test. That is, it requires a user to speak about 10-second voice to their smartphone every day to get PD detection. However, this kind of active sensing solution ignores the significance of the user compliance. And statistics show that about 50% users will totally give up after 1 week. So such active sensing solution cannot continuously access human condition. And for about a passive sensing, the challenge is we will not allow a remote medical center to continuously monitor our phone talk if the privacy cannot be guaranteed. So our hypothesis is that since Parkinson's disease affects our vocal organs, if those privacy-irrelevant non-speech body sounds can, as well as voice, contain the PD biomarkers, if that works, we can develop a system that leverage our smartphone to extract and transmit only non-speech body sound. For example, the breathing sound, sniffing sound, to remote medical center get a PD detection. To validate our hypothesis, we developed PDVocal, a smartphone system that includes a smartphone end and a cloud server end. So let me first introduce the implementation at the smartphone end. To collect data, we still use a voice test-based solution to collect data. But the difference is we try to wake up our microphone a few seconds before the test begins. In this way, we successfully extract some non-speech sounds, for example, breathing sound, cleaning throat sound, from this stop-up phase. And we label the data from the pre-stop-up phase as the non-speech body sound, and we label the data from the testing phase as voice. And we adopt the mobile net as a classifier due to its high efficiency and low latency at the smartphone end. And we can achieve about 90% average accuracy to differentiate non-speech sounds and voice. We also evaluate the resource cost of our privacy isolation zoo at the smartphone end. And the results show that it is possible to run our system in real time. And after transmitting the data to the cloud server, first, we adopt the spectrogram representation to augment features in both time and frequency domain. And then we adopt a convolution network to achieve the PD detection. We specifically adopt a 10-layer residual network that achieves the best performance on our data set. And to evaluate the PDVocal, We collaborate with medical centers and enroll about 890 subjects from the United States. And every subject is evaluated by the UBTRS, and there are about 321 PD patients, and the remaining people are healthy people. Also, demographic information is surveyed for each participant. And we totally extract about 14,000 samples, and we design 3 groups of experiments. First, we compare the performance between voice and non-speech body sounds. So we found that non-speech sound can achieve about 83.3% average accuracy that is close to the value using voice. This result shows that non-speech sounds and as well as voice can contain the PD biomarkers. Second, we compare the performance between early stage and mid-stage patients. The difference is about 1%, showing that our system can work for patients in both stages. Next, we evaluate the impact of the user demographic and the user behavior on PD detection. On the whole, our system appeared to be general on different user conditions. So this is all about our story on smartphone dataset, but we do not stop here. And our vision is if social networks become the largest chronic disease screening site. So we try to collect some data from the YouTube, and we use the keywords Parkinson disease voice disorder, and we find 5 patients with PD. And we try to directly use our pre-training model in smartphone dataset and evaluate on the public available dataset. And we can achieve about 91.3% accuracy on healthy people, and we can achieve accuracy about 58.2 on patients with PD. It seems that our system will have some bias to predict patients from the YouTube. That is, it will more likely predict a subject as the healthy people. But still, I think our system can still work as a first defense to remind the user to go to a clinical diagnosis. Finally, let me summarize our contribution. First, we studied the relationship between Parkinson's disease and non-speech body sounds. Second, we designed a privacy-preserving and a passive sensing system. Third, we evaluate on a smartphone dataset and public available social media data. That's all about my presentation. Thank you.